Welcome, fellow developers and IT enthusiasts. Have you ever found yourself painstakingly crafting Docker files for your Java microservices, trying to balance image size, build speed, and security? It's a common challenge, and honestly, the process can be tedious and prone to human error. Often, what you end up with is a functional but not truly optimized Docker image, perhaps bloated, slower to build, or with potential security vulnerabilities. This manual optimization often takes valuable developer time away from core feature development, leading to bottlenecks in deployment pipelines. But what if there was a way to automate this, to leverage the power of artificial intelligence to analyze your project and recommend, or even generate, the perfect Docker file for your needs? Imagine a world where your build process is not just automated, but intelligently optimized. Today, we're diving deep into an innovative concept, accelerating Java microservice deployment with AI-driven Dockerization. We'll explore how generative AI tools can revolutionize the way we build and deploy Java applications, making the process faster, more secure, and inherently more efficient. Get ready to see how AI can transform your DevOps workflow. So, what exactly do we mean by AI-driven Dockerization? At its core, it's about shifting from manual Docker file creation to an intelligent, automated process where generative AI plays a central role. Instead of a developer manually writing from, copy, run commands, an AI system analyzes your project's characteristics. Think about it, your Spring Boot version, Maven dependencies, Java version, and even your application's runtime behavior can all influence the ideal Docker file. A sophisticated AI could ingest this metadata, compare it against a vast knowledge base of Docker best practices, security guidelines, and performance considerations, and then output a highly optimized Docker file. This isn't just about syntax completion, it's about intelligent decision-making, recommending multi-stage builds, lean base images, proper user configurations, and even JVM tuning parameters specifically tailored for your application. This approach ensures consistency across your entire microservice ecosystem, reduces cognitive load on developers, and significantly accelerates the path from code commit to production-ready container, turning a complex, iterative task into a seamless, intelligent automation. To illustrate this powerful concept, we've prepared a straightforward yet effective demonstration. Our subject for today is a quintessential Java Spring Boot microservice. It's a very simple, Hello World, REST API, built using Apache Maven, which exposes a single endpoint at /API/hello that returns a friendly greeting. While this specific microservice is intentionally basic to keep our focus on the Dockerization process, it perfectly represents any typical Java application you might be working with. The principles and optimizations we're about to discuss are universally applicable, whether you're building a complex data processing service or a simple user authentication API. The key takeaway here is that regardless of your Java application's complexity, the challenge of creating an optimal Docker file persists, and that's precisely where our AI-driven solution shines. We'll be showing you how to take this simple Spring Boot application and transform it into a highly optimized Docker image, not by hand, but with the intelligent assistance of AI. The real brains behind this operation, at least conceptually, is our AI recommendation script. In a real-world scenario, this would be a sophisticated generative AI service, perhaps powered by a large language model fine-tuned for code generation and optimization. For our demonstration, we've simulated this with a Python script named recommend_dockerfile.py. This script isn't calling a live LLM, instead, it contains predefined logic that mimics the analytical capabilities of a Gen AI tool. It understands that we have a Java Spring Boot application, identifies common optimization patterns, and then programmatically generates the content for our Dockerfile.recommended file. The simulation highlights how an AI could analyze project characteristics like the Java version, framework, and dependencies. It then intelligently applies best practices such as recommending a multi-stage build, proper layer caching strategies, and even security enhancements like running as a non-root user. This script acts as our intelligent assistant, taking the guesswork out of Docker file creation and ensuring that the generated file is not just functional, but truly optimized for our Java microservice. Now, let's peel back the layers and truly appreciate the magic of the AI-recommended Docker file. One of the most significant optimizations is the multi-stage build. Traditionally, developers might build their Java application and then copy the resulting JR into a runtime image. The problem? The build environment, often a full JDK, ends up bundled into the final image, making it unnecessarily large. Our AI-driven Docker file elegantly solves this by defining two distinct stages. The first, aptly named build, uses a JDK base image, specifically Eclipse Temurin 17 JDK focal. This stage is where all the heavy lifting happens, compiling your Java code with Maven, downloading dependencies, and packaging your application into a lean, executable JR file. Once that JR is ready, the final stage kicks in. This stage uses a much smaller, production-ready JRE base image, Eclipse Temurin 17 JRE focal, which contains only the Java runtime environment, not the entire development kit. Crucially, we then copy, from =build the artifact, transferring only the necessary JR from the build stage to the final runtime image. This separation dramatically reduces the final Docker image size, minimizing its attack surface and accelerating deployment. Beyond size reduction, our AI-recommended Docker file also excels in optimizing build speed through intelligent layer caching. This is critical for frequent CI/CD cycles. A common pitfall is copying all source code at once, which invalidates Docker's build cache every time a single line of code changes. Our optimized Docker file addresses this by strategically copying files. First, it copies only the pom.xml file. Why? Because pom.xml defines your project's dependencies, and these dependencies change far less frequently than your actual source code. After copying the pom.xml, the run mvn dependency, go offline command is executed. This command downloads all required Maven dependencies into the Docker build cache. By separating this step, Docker can cache the dependency download layer. If your pom.xml hasn't changed, subsequent builds will reuse this cached layer, skipping the potentially time-consuming dependency download step entirely. Only then is the rest of your src directory copied. This layered approach ensures that only the necessary layers are rebuilt when code changes, leading to significantly faster iterative builds and a more efficient development workflow. The AI understands this subtle but impactful optimization, implementing it automatically for you. Security and runtime performance are equally critical considerations for Java microservices, and our AI-generated Docker file makes intelligent recommendations in these areas too. A paramount security practice is to run your application as a non-root user inside the container. By default, processes in Docker containers often run as root, which poses a significant security risk. If a vulnerability were exploited, an attacker could gain root access within the container, potentially escalating privileges. Our Docker file includes commands to create a dedicated Spring user and group, and then switches the user to Spring before running the application. This adheres to the principle of least privilege, dramatically reducing the potential impact of a container compromise. Furthermore, the AI understands the nuances of running Java applications in containerized environments. It recommends essential JVM tuning parameters via the Java_OPTS environment variable. These include XMS and XMX4 setting initial and maximum heap